Hi everyone, I'm Adnan.
I'm Cali.
I'm Kenneth.
And I'm Shane, and this is our PowerPoint presentation on our improvements to our puck light assembly. So here's the outline of our presentation. We're going to start with the initial design overview, and then discuss the issues with the initial design. And then we'll go over the industrial engineering tools we used, the major problem that we are exploring, the metrics that we use for improvement, the initial design, our potential solution, and the implementation of the solution, an improvement check, and then we'll discuss other design changes for improvement.
So these videos show the current process that's in place. As you can see, they're all happening simultaneously to show what would be happening in the assembly line. This is supposed to have a takt time of 28.8 seconds, but as you will see, workstation number 3 exceeds this takt time and therefore requires 2 workers to do this task. So using the concepts of manufacturing design that we discussed in class, we noticed several flaws with the current design, which we will later explore in greater detail. These include unclearly asymmetrical parts, parts that are very small, screw fastening, restricted access, non-interchangeable parts, as well as over-constrained parts. So we will first look closely at solving problems associated with the parts that are very small and restricted access.
So a few industrial engineering tools that we are going to use in our solution are 5S methodology as well as lean manufacturing. So the 5S methodology has 5 pillars, and they are sort, set in order, shine, standardize, and sustain. And for sort, it says to remove items that are not needed for production. Set in order says to arrange items so they are easy to use. So for our project, we had all the parts organized into bins so that they were easy to access. And for shine, it says to keep everything swept and clean. So we made sure that the workbench for the workers was always neat and tidy. For standardize, it says to ensure that there are common standards and ways of working. So we made sure that our process followed the line balance that we created in Lab 1. And for sustain, it says to properly maintain correct procedures. So we always made sure that the processes stayed the same.
So lean manufacturing works on the basis of 7 muda, which roughly translate from Japanese to wastefulness, 2 of which we found particularly applicable in the case of this project. The first is waiting. So this is waiting for the next step in production. It wastes time on the assembly line. You find your assembly line workers idle, and that's not good because it decreases the efficiency of the process. This can be mitigated by properly balancing the line, which is exactly what we did for this iteration of the assembly line. Overprocessing is the other issue. So this results from poor tool or product design. It creates extra activity and it leaves your workers performing more actions than may strictly be necessary. So in the case of our assembly line, more small screws were used than were necessary. This is a problem we confront later, and we will come up with a solution for them.
So one of the major problems that we're focusing on is issues with the small screw. So these small screws are really difficult to handle, and it causes the employees to fumble them a lot more often. These screws also require really precise precisioning, so they must be perfect in place in order to fasten them. They're also difficult to fasten, so the holes are really restricted, and it requires the screwdriver to be planted firmly at all times while fastening.
So in the few upcoming slides, we're going to discuss the metric that we use to measure our success. So just a side note, in order to measure our success, we had to use multiple metrics. So the 2 metrics that we use to define our success is task time and assembly cost. So we define task time as the average time taken to complete the task of fastening all 4 of the small screws, and assembly cost as the cost of assembly, which is composed of employee wage, cost of extra tools, etc.
So on the left is a video of the initial screw assembly process. In this process, the worker aligns a screw with a screwdriver head, aligns that screw with a hole in the flashlight, and fastens the screw. This process is repeated a total of 4 times. So on average, this process took 35.18 seconds, which we found through the course of 30 trials of this process. So the current cost of this, the main cost is associated with paying the employees. Employees are paid $400 per week each. The original design requires 5 employees for a total cost of $2,000 per week. The reason that costs for supplies have not been taken into account is because, for the most part, those costs are going to remain constant between the old process and the new process. The only time we're going to account for the cost of supplies is in the difference, if we find out that we've decided to change some of the pieces associated with the assembly, in which case we will only account for the difference in cost there.
So the next few slides are going to discuss the potential designs that will improve our metrics of task time and the costs. So our first idea to improve the metrics was to remove the excess constraints with these screws. So in the left image, the battery casing is held in with 4 screws. We think that that was unnecessary and that it only needs the 2 screws. So in the right image, it shows just the 2 diagonal screws that are needed to hold it in place.
Continuing with the previous idea of only 2 screws in the flashlight, we came up with this solution. So what it is a screwdriver that features a comfortable grip handle, 2 Phillips screwdrivers in one, and magnetic tips for easy alignment. What this solution has to offer is it allows the employees to handle the smaller screws less and align them easier. So diving into the mechanics behind the tool, essentially the way that it works is that there are 2 belts connected to the inner gear and to the outer gears. So what happens is that the employee will turn using the handle, and in return it will then turn the other 2 gears in order to fasten those 2 screws. What this does is this cuts down the time that it takes to fasten, but keeps the alignment time the same.
So as Adnan had discussed earlier, the benefits to this solution would be that it reduces the handling of the small screws. It also eliminates extra activity by eliminating 2 screws, which would eliminate any over-processing. And it also standardizes the task by using the tool for every employee. So now, using the metrics that we previously discussed, which were task time and cost assembly, we'll check to see if our new tool caused any improvements. And if no noticeable difference has been taken place with the metrics between our new tool and our previous design, then we'll have to do iterative design.
So for the task time improvements, we took the task of fastening the small screws into the holes and broke it down into 3 subtasks. The first of these subtasks was the screwdriver screw alignment. So we aligned the screw with the head of the screwdriver. Because the head of the screwdriver was magnetic, this would stay on for the duration of the task. Next was the screw hole alignment, in which we put the small screws inside the holes. Finally, the fastening, where we rotated the handle of the screwdriver until the screw was tight in the hole. We took 30 of these trials for each of these subtasks in order for our results to be safe, to provide a good average. So, looking at this in comparison to our new tool that we designed, the new tool will require twice the screwdriver screw alignment time, which makes sense, because you have to put 2 screws on the head of 2 screwdrivers effectively. The tool will require twice the screw hole alignment time. Again, this makes sense because you have to align and screw into a hole twice. However, where the tool saves time is because it only requires the same amount of fastening time in order to fasten 2 holes. The expected results from the tool work out to 15.29 seconds in order to accomplish the task of fastening the small screws. This is an improvement from our 35.18 seconds from our current process of fastening 4 screws into the holes, each doing it individually with a screwdriver. It saves 19.89 seconds. So quite a few improvements were made in terms of the assembly cost. First off, there was an estimated cost to build this tool that we've proposed to insert the small screws. The handle and the steel will cost about $14. The 3 gears will cost $8.91. The 2 rubber belts, $8.04 for a total of $30.95. We priced this all out on Amazon. Now the expected employee costs. The employee salary remains constant at $400 per week per employee, but there are improved weekly costs. Because we've cut the assembly line from 5 employees to 4, $400 a week are saved, leaving your employee costs at only $1,600 a week. Additionally, because we've cut 2 screws from the assembly, this saves approximately $1,200 a week, assuming you're producing 5,000 flashlights. So for the total savings, in the first week, you save $1,569.05 because we assume you had to purchase the materials to produce the tool in that first week, but we assume that their costs of maintaining the tool are negligible. So for future weeks, it's $1,600 a week that you've saved.
So here's a side-by-side of 2 videos of the screw assembly. On the left, it is the initial design of screwing in each screw individually. And then on the right, it's a simulation of screwing in 2 screws, which will be done by the tool that we developed. So as you can see, the time on the right was significantly less than on the left, which was the initial design.
So now that we've discussed how we confronted the design issues from the over-constraint provided by the 4 screws inside the flashlight, we will be discussing some additional improvements which can be made to the product if one wishes to further investigate with the design. First, asymmetrical parts, which are not obviously asymmetrical. They should be either symmetrical or obviously asymmetrical. Second, interchangeable parts. There are screws of 2 different sizes. It would be easier if there were screws of 1 size. Finally, there is restricted access present in the back of the flashlight near the battery casing.
The first improvement that we'll look at is adding symmetry to asymmetrical parts. So the part in particular is the panel in the front frame of the flashlight. This is of asymmetrical nature, and so what we suggest trying to do for this is to make the front frame slightly smaller and add a circular disc similar to this, which would allow the panel to sit inside the front cover, similar to the other original design. However, it won't need to be positioned properly. For our next improvement, we'll do similarly to what we did in the last slide. We'll remove asymmetry, but this time we'll add clear asymmetry to the product. So this is the reflector plate for the bulbs. What we suggest doing is arranging the holes for the bulbs in a diamond shape in order to allow the employee to place it in one of 4 ways that are obvious.
In order to produce our interchangeable parts for the flashlight, we propose that all screws are of the same size in order to reduce the waste as well as the processing associated with picking the screws. So as you can see on the left, the 2 screws on top are for the outside plate, and they obviously do not match the size of the smaller screws. This plays into the idea behind handling the screws, as one is easier than the other. However, on the right, all screws are the same size. Obviously, this would come with a little bit of a modification for the design, but can be done.
So creating unrestricted access is important because it makes it easier for the employee to insert the screws into the screw holes. So as it is, the employees have to effectively reach into a small crevice with a screwdriver and then squint to line it up with a hole because it's kind of dark in there. However, with the design that we propose, there would be unrestricted access because it would be flush with the backing of the light fixture. In order to compensate for this extra height, we would drop the battery casing further down inside that back plate. So by further investigating these design concepts and implementing them in the process, we believe that there could be drastic improvements made to the factory process. Thank you for watching.